Okay, we're on section 7, which is inverse trigonometric functions. If you haven't used them, you've probably seen them on your calculator. They're the ones that say sine minus to the minus 1 power. And the minus 1 doesn't mean the inverse. It means, well, it doesn't mean the inverse. It doesn't mean the reciprocal. And remember, we've already talked about some inverse functions. Let's see if I have that on the next page. No. Okay. So one of the main ones that we've looked at are e to the x and the natural log of x. And those are inverse functions as well. And what we know is that f of g of x equals x. So e to the natural log of x is equal to x. And the other way, g of f of x is equal to x. So that's the natural log of e to the x, which is just x again. So those are mathematical properties of inverse functions, and we have similar ones for trig functions. Now there was a requirement for functions to be able to be inverses of each other, and one of them was that the functions had to be one-to-one. So they have to be one-to-one functions. What does that mean? It's kind of like, it's one way you could say is it passes both the horizontal and vertical line tests. That's another way of saying that for each x there's one y, and for each y there's one x. We could write that out, but that's what that means. Now the problem we have is that, say for example, the sine and cosine functions, say the sine function looks like this, and you can see that for each value y there's an infinite number of values of x, because every time you go through a period you get two of those values, just like you get the coordinates repeating themselves on the unit circle. So we'll come back to that in a second. So before we do that, though, if at this point we've talked about what the values of certain angles are in either radians or degrees. So we know that the sine of pi over 3 is the square root of 3 over 2, or the sine of 60 degrees is square root of 3 over 2. So if you went the other direction, if you said what angle has a sine of the square root of 3 over 2 instead of what is the sine of pi over 3, here you get, for each value of x, there's always just one value of y. But the thing is, here, for each value of y, there are multiple values of x. And the way you could answer that question is by just taking a horizontal line that is at the y value that they're asking about. And the y value here would be 0.866, the decimal equivalent of the square root of 3 over 2. So here's 1, and here's a half. So if you can see the I don't know if you can see the scale, but that's 0.6, 0.7, 0.8, about halfway up. And what you would do is you'd come over here and you'd say, okay, this value of y, what's the value of x? You come down to the x-axis and you'd find pi over 3. That's this that goes along with this solution. But there's also one here, 2 pi over 3, and then this would be 7 pi over 3, I think. This would be 8 pi over 3. So there are an infinite number of results to that or answers to that question. But what if, let's say, instead of having the entire sine function, we restricted the domain and we said what angle has a sine of the square root of 3 over 2 between negative pi over 2 and positive pi over 2. So what that would mean is we would pretty much mark out the sine function and only worry about it between here and there. So they coincide between negative pi over 2 and positive pi over 2. but between, so here to here. And so if I ask this question, there'd be one answer. The answer would be this first intersection. So put a question mark. The answer is pi over 3. Okay, there's one answer. And one thing we can say about the sine function between negative pi over 2 and positive pi over 2 is that for every value of x, there's one value of y, and for every value of y, there's one value of x. So that means we could have an inverse function of the sine function if we limit the domain that we're looking at. So here were some questions we've already talked about. What is it called when a function has one and only one value for x and y for each value of x, and one and only one value for y for each value of x? And we said that was, what that's called is, it's called 1, 2, 1. How about the sine function? No, sine function is not. But if we restrict the domain to the values between negative pi over 2 and positive pi over 2, then it is. So we can say yes then. So the sine function does have an inverse function on the restricted domain from negative pi over 2 to positive pi over 2. The terminology we use, we have two ways of representing that inverse function. One is sine with the negative 1 to the negative 1 power of x. We also have this one called arc sine. I don't know if this was done because if you did in the old days, if you didn't have a typewriter that could do exponents, maybe it was easier to write this one. I have to look into the history of why they have the different meanings. So looking at this previous problem, what is the arc sine of the square root of 3 over 2? So if I said, or the inverse sine, so the inverse sine of the square root of 3 over 2 would be pi over 3. Instead of saying the inverse sine, sometimes what we're really doing is saying what is the angle whose sine is the square root of 3 over 2, restricting the angle to negative pi over 2 to positive pi over 2. And you can also do it in degrees, negative 90 degrees to positive 90 degrees. So when you use the inverse trig functions on your calculator, you're going to, you have to worry about mode, depending whether you want the answer angle in degrees or radians. But it's valid either way. By the context of the problem or by somebody stating something, you can say whether the answer should be in radians or degrees. Now, the answer it's going to give you is not the square root of 3 over 2. So if I plug this into my calculator, so I'd say inverse sine of the square root of 3 over 2. So I'll turn my calculator on. So I take the inverse sine of the square root of 3 divided by 2, and I had it in degrees, so that did come out exactly 60 degrees. But if I change the mode to radians, which I forgot to do, and I do the inverse sine of the square root of 3 divided by 2, I get 1.047195 blah blah blah, which doesn't look like pi over 3. But if we were to take 1.047197 divided by pi and multiply by pi, so we leave that number in our calculator. We don't write it down because we'd lose accuracy if we did that. So we want to keep as many decimal points as possible. Divide by pi, and you'll get 0.333333333 10 threes, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 1/3, which this therefore becomes 1/3 pi, or pi divided by 3. So that's one thing that we're going to do a lot of, is converting the decimal numbers you get out of your calculator into some fraction of pi. And why am I doing that? Well, one thing is because it allows you to not have to memorize the unit circle. Okay, so if you don't want to do that, you can, well, even if you wanted to, you can't do it. So, okay, so we already talked about that, and we talked about that. Well, let's see. So for the inverse sine function, y equals the inverse sine of x if and only if the sine of y equals x. So that's just kind of defining that these are inverse functions of it. And you can kind of say that they're equivalent to each other. So if you said the inverse sine of the square root of 3 over 2 is equal to pi over 3, that's the same as saying the sine of pi over 3 is equal to the square root of 3 over 2. It's kind of like when you were doing logarithmic and exponential stuff. You know, we used to say, what's the equivalent if you had e to the 2 equals, well, let's do something other than e, so if you had 4 to the 3rd power equals 64, that's the exponential form. The logarithmic form would be log base 4 of 64 equals 3. So the same thing applies here. This is the inverse sine version. This is the sine version. And we already talked about that. So you can, you know, with inverse functions, you can also, another way of thinking about it is all you do is you just switch the x and the y's. So here what I have is theta. Here's the sine of theta. So for 0 and these values, these are the sines of those angles. So if you took x as the variable, and that's, so this is the x value now, this was the y value, so switch the x and y values. So if x equals 0, the arcsine of x is 0. The arcsine of a half is pi over 6. The arcsine of the square root of 2 over 2 is pi over 4. So you just switch. That's another characteristic of inverse functions, is you flip the numbers. And that's also why they are symmetric around the line y equals x, which we'll see later. Okay. So here is the sine function. We've been drawing 2 full periods of the sine function, but because we have to restrict the domain to make it 1-to-1, we're only going to look at from negative pi over 2 to positive pi over 2. Now you might say, well, why don't we restrict it from 0 to pi instead? That seems to be easier if we started at 0. But the thing is that if you did that, it would still not be 1-to-1. You know, if we looked at the sine function from 0 to pi, it would look something like that. And so it's not 1-to-1 in that case. And then so the only option that makes any sense is to do it between negative pi over 2 and positive pi over 2. So this is the sine function. I think what I have on the next page is the inverse sine function. So there you go. There's the blue curve is the inverse sine function. Notice over here, for the sine function, the domain is what we specified it as. So here it's from negative pi over 2 to positive pi over 2. The range is from negative 1 to positive 1. Okay, that's so here it's negative 1. Here it's positive 1. So with inverse functions, the domains and ranges switch. So the domain of the inverse trig function is from negative 1 to positive 1, and the range is from negative pi over 2 to positive pi over 2. So when you use your trig function, when you use the inverse sign on your calculator, you're going to get answers. The answers are the range between negative pi over 2 and positive pi over 2. And this, from negative pi over 2 to 0 is the fourth quadrant. But it's not the fourth quadrant that we normally think of, where we go around counterclockwise. We're going the other way. So let's just use our calculator to show that's true. Okay, so let's say we want the inverse sine of plus 0.5. So if we do that, and let's go ahead and do this in degrees. So change your calculator to mode to degrees. Okay, so if I do the inverse sine of 0.5, I'll get 30 degrees. If I do the inverse sine of negative 0.5, so inverse sine of negative 0.5, I'll get negative 30 degrees, which this is equivalent to positive pi over 6. This is equivalent to negative pi over 6. So that's why you get positive and negative answers for the sine. But the thing is, a lot of times, we want to know the answer from 0 to 2 pi. So we somehow have to take this information and get it so that we can apply that. But we'll talk about that later. Okay, here's the line y equals x, and you can see how the two functions are symmetric around this line y equals x. So it satisfies the normal requirements for inverse functions. Now the cosine function, what we're doing here is we're going to limit the domain not from negative pi over 2 to positive pi over 2, or from negative 90 to positive 90. We're going to restrict it from 0 to pi. And again, that's because of the way the cosine function looks. Again, we got a lot of practice at drawing that. It looks like this, comes back up. On the other side, it goes like this, comes back up. And so if we were to choose negative pi over 2, which is here, to positive pi over 2, you can see the function is not 1-to-1. So that wouldn't help us any. So what we do is we limit the domain from 0 to pi, and you can see that it is 1-to-1. It takes on both positive values and negative values. So when you use the inverse cosine or the arc cosine function in your calculator, you're going to only get answers between 0 and pi. Now here is the two functions. This is the red curve is the cosine function, and the blue curve is the inverse cosine function. I've erased a little bit here just because of the way the graphing program works. But again, you can draw a line. I don't know if it's on the next sheet or not. Yeah, you can draw a line, the line y equals x, and you'll see that these are symmetric around this line. Sometimes this is on this side, blue's to the left, red is to the right, and then it flips, but they're always symmetric like that. So let's just reiterate. So again, if we go back here, the domain and the range for these things, the domain of the cosine function is limited on purpose between 0 and pi, and the range is between -1 and +1, just like the case for the sine function. This inverse sine function here, its domain, so this is for the arc cosine of x. The domain for that is from -1 to +1, and the range is from 0. So let me, I should have made that x over here. So since we're talking about domain, it's x. Here, y is between 0 and pi. And we'll just demonstrate this using our calculator. So if I were to do the arc cosine, or the inverse cosine of 2, and I plug that in my calculator, the arc cosine of 2 is error. Why is that? Because 2 is not in the domain of the inverse cosine function. If I did the inverse cosine of 0.5 again, and let's see what I have, let's see what mode I have here. I'm in degrees. So if I do degrees, inverse cosine of 0.5, what angle has a cosine of 0.5? The answer would be 60 degrees, or pi over 3. And if I did the inverse cosine of negative 0.5, so I do that, inverse cosine of negative 0.5, I get 120 degrees, or 2 pi over 3. And what's happening there is, in terms of the unit circle, we're saying, where in the unit circle do I have an x value of positive 0.5? Well, I have two values. One's in the fourth quadrant, which is not in the domain, so the only one that works is this one here, that's pi over 3. And then if I go to halfway here, which angle has a cosine of 0.5? It has an x-coordinate. It's going to be this one. So that's the angle. That's 2 pi over 3. Again, there's a third quadrant solution, but that's not it's not in my range. So I can't get it. So you get a number between 0 and pi, or 0 and 180 degrees for the cosine. And again, so how do you use that information to find solutions at anywhere in the unit circle? Or how do you use it to find all the solutions? Well, that's a chapter 5 thing to do. And this is what the okay, so then we have the tangent. So we've done the sine, inverse sine, cosine, inverse cosine. So here we're plotting the y equals the tangent of x. So this is the last one we're going to do. The cosecant, secant, and cotangent we really don't worry about. Those are not on our calculator. We can always manipulate it to get the answer we need. So just for an example, if I had the arc secant of 2, that would be the same as the arc cosine of 0.5. So if I get something this form, I can always just take the reciprocal of the argument, and I can get the answer that I need. So we don't worry about what they look like. Okay. So the tangent function, you have this repeating thing. We have vertical asymptotes on either side. The function exists between negative pi over 2 and positive pi over 2. Notice I don't have equal things here, and that's because at those two values of x, the function does not exist, because you're dividing by 0. So the domain is slightly more restrictive. I almost did it on purpose there. Or I didn't do it on purpose, but you get so used to putting the equals, less than and equals and greater than equals. So that's the domain. And you can see that with that domain that the function is 1-to-1. For every value of x, y, there's one value of x. For every value of x, there's one value of y. So it makes it 1-to-1. So that's the domain. That's the restricted domain. And the range for the tangent is negative infinity to positive infinity, and not including it. If you go closer and closer, you get to negative pi over 2. The closer you get to negative infinity, and the closer you get to positive pi over 2, the closer you get to positive infinity. So that's the domain and range. Now the blue curve here is the inverse tangent function. So for the inverse tangent function, the domain is negative infinity to positive infinity, and the range is negative pi over 2 to positive pi over 2. So whereas the cosine, we couldn't take the inverse cosine of a number greater than 1 or a number less than negative 1. For tangent, you can take the inverse tangent of any number. It'll give you an answer. And if I plot the line y equals x, again, you can see how they're symmetric across that line. So it has all the characteristics of an inverse function. So that's just a demonstration here of how it works. So the inverse tangent function, so if you did the inverse tangent of 0.4, and you plug that in your calculator, and make sure it's, since it's a decimal, it's probably a radians, but they'd have to specify what it is. Or somebody would have to specify what it is. Okay, so I'm going to put in radians. So if I do the inverse tangent of 0.4, that is 0.3805 radians. If we multiply and divide by pi, we get 0.1211 pi radians. So let's say I did the inverse tangent of negative the square root of 3 over 2, square root of 3 over 3. Well, because the way the domain is set up, when you have a negative, taking the inverse tangent of a negative number, you're going to get a negative angle between negative pi over 2 and 0. So if we take the inverse tangent of negative square root of 3 divided by 3, close parentheses, we get negative 0.52358, blah, 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 blah. So that looks kind of like that, but we know this is one of those special angles, so it's either going to be a half, it's either going to be pi over 6, pi over 4, or pi over 3, negative. So what we'll do is we'll take that decimal number, which we'll leave in our calculator so that we get maximum accuracy, divide by pi, multiply by pi. So we have the answer divided by pi, and that's all we do. We don't multiply by pi because we're going to have it explicitly shown here. So we just take that answer, divide by pi, and you get negative 0.16666 blah, 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 pi. So that's going to be negative pi over 6. So that's how that works. If this were in degrees, I'd get negative 30 degrees. So here are all the different ways you can deal with inverse functions. And if you take the sine of the inverse sine of x, it's x. So we've got a sine and inverse sine. If we take the inverse sine of the sine of x, then we get x. That's just the properties of inverse functions. The cosine of the inverse cosine of x is x. The inverse cosine of the cosine of x is x. But if you mix them up, the inverse sine of the cosine of x does not equal x. So we have some homework problems where you just have these simple cases. If I said, what is the cosine of the inverse cosine of 0.6, the answer would be 0.6. If the function and its inverse are matched together, the answer is just whatever is in the original argument of the inverse cosine. And you could do the same if you did what is the inverse cosine of the cosine of pi over 6. The answer would be pi over 6. Now sometimes we get kind of these other types of combinations that you deal with. So let's say I have the sine of the arc cosine of 1/2. So here we do have the mixture. I said it's not equal to x, or it's not equal to a half. This does not equal a half. But it does equal something. I mean, it does exist. So the question is, how do you figure out what that is? Well, the easiest way is to make up a right triangle and use this information to construct the triangle. And then once you have all three sides, then you can take the sine of the angle knowing the three sides. So that's the basic concept. So this is write theta in terms of the triangle and the inverse trig function. So you got a couple of these on the homework. So what you're given that the sine of theta is x plus 2 or 5. The question is, what is the basically, how do you solve for x? That's what they're asking for. So how do you write theta in terms of, how do you make this into theta equals something? So what you can do, in this case we don't actually have to fill in the triangle because of the question they're asking. So if you look back to solving exponential equations, let's say we said e to the 2x equals 7. So what is x? Just like x is in the argument of the sine function here. Here x is in the exponent. So what we did is we said, okay, let's take the natural log of both sides. The natural log of e to the 2x is 2x. And then you divide both sides by 2. So you get x is the natural log of 7 divided by 2. So the same kind of thing here. You take the two inverse functions that match up. So you take the arc sine or the inverse sine of the sine, which is just the argument, just like natural log of e to something is the something. So the arc sine of the sine of theta is theta, and you take the arc sine of the right-hand side as well. You're doing the same thing to both sides. And so that's your answer. So you can write it as theta equals arc sine of x over 2 plus 5. Or theta equals the inverse sine of x plus 2 over 5. So that's, in this case, you didn't really need to draw the triangle. Yeah, we'll come back, and we don't cover this in the next section. So that's what's leading to here. In some ways, that's what we did here. We used this similar type of reasoning. But here we are. How do you evaluate the tangent of the arc cosine of 2/3? We're asking, what is the tangent of the angle whose cosine is 2/3? 2 over, is that 2/5 or 2/3? What is the angle of the tangent of the angle? So, yeah, I need to be consistent here. Which one did I use? I guess this should be, I don't know why I did that. So this is, should be 3/5. What is the tangent of the angle whose cosine is 3/5? So you create this right triangle, and you say let theta be the angle whose cosine is 3/5. So for this part we put in theta. So inside the argument, the tangent of theta, where theta is the arc cosine of 3/5. So we say, okay, let theta be the angle whose cosine is 3 over 5. Well, remember the cosine is the length of the opposite adjacent side to the opposite side. So I can use this fraction to specify the length of the adjacent side, 3, and the hypotenuse, 5. And if you solve for the other side, for the opposite side, this squared plus that squared equals that squared. And so in this case, we don't know what this is at this point. We'll call it x. So 3 squared plus x squared equals 5 squared. So you get 25 minus 9, 16. Take the square root and you get 4. So now I fully define the triangle, and then I can find any of the trig functions. The one they're specifically looking for here is the tangent. So the tangent of theta, which is the opposite side length of the adjacent, is 4/3. So let's add a page here. So when somebody asks you this, what is the tangent of the arc cosine of 3/5? The answer is 4/3. But you have to go through this whole triangular thing. And when the arguments are positive like this, it's easy to kind of put it in context of a right triangle. Now, let's say if they had the arc cosine of negative 3/5. How are we going to do that? Well, we'll talk about that. Here's another one. What is the sine of the angle whose cosine is the square root of 5/5? So we let this thing be called theta. So theta is the arc cosine of the square root of 5/5. The cosine is the hypotenuse over the adjacent over the hypotenuse. So we draw our arbitrary right triangle here, our illustrative or representative, maybe that's a good word, representative. So this is the numerator, that's the length of the adjacent side. The denominator is the length of the hypotenuse. So what we would do is we need to figure out what x is. So again, the Pythagorean theorem says 5 squared plus x squared equals the square root of 5 squared plus x squared equals 5 squared. X squared is equal to 25. So you get 5 plus x squared. X squared equals 20. X equals the square root of 20. So that's x is that. And so then if we want to find the sine of theta, well, theta is defined by this right triangle with the given side lengths now, and that is the opposite over the hypotenuse. The opposite is the square root of 20. The hypotenuse is 5. So that's your answer. We could factor out a 4. So 20 is 4 times, square root of 20 is 4 times 5. The square root of 4 is 2. So you get that. So the angle, the sine of the angle whose cosine is the square root of 5/5 is 2 times the square root of 5/5. Okay, here's another one. Now, here's the tricky part. We've got a negative. Now, in this case, we're okay because both of these have the restricted domain of from negative pi over 2 to positive pi over 2. When the sine is negative, the tangent is negative. If you think about the two functions between negative pi over 2 and positive pi over 2, the sine looks like that. The tangent looks like something like that. And so these are both negative and these are both positive. So what we do is we create a triangle with the lengths, but we don't assign the negative to it. The negative just tells us that it's in the fourth quadrant. And we know they're both the same sign. So if the sine is the trig function, if the sine is negative 3/4, then the tangent is also going to be negative. So we say theta in this case is going to be the angle whose sine is 3/4. So we're using the positive because it's a right triangle. It's lengths. So this is our unknown length. X squared plus 3 squared equals 4 squared. X squared plus 9 equals 16. X squared equals 7. X equals the square root of 7. So that's what that is. 9 plus 7, 3 squared plus 7 squared is 16. The square root of 16 is 4. So that's what that is. So if I want to take the tangent of theta now, so now that I have all three sides defined as far as their length is concerned, the tangent of the angle theta is going to be the opposite over the adjacent, which is 3 divided by the square root of 7, which when you multiply and divide by the square root of 7, you'll get 3 square root of 7 divided by 7. So the answer here is 3. Well, okay, now I almost forgot about the negative sign. But if I do this, if I say the tangent of the arc sine of negative 3/4 is actually negative square root of 3. It's 3 square root of 7 over 7. So that's where the negative comes back in, is when I do the complete expression. The right triangle gave me the magnitude. The quadrant that I'm in gives me the sign. Okay. This is just reiterating, because we limited the domain on the sine, the range of the inverse sine is limited. So as I said earlier, for the sine function, the answers are in the first quadrant and the fourth quadrant. The cosine is in the first quadrant and the second quadrant, and the inverse tangent solutions are in the fourth quadrant and the first quadrant. Just think about what I'm doing here. Okay, just refresh my memory. Okay, so these just practices. This is to just demonstrate what is actually going on. If I said, what is the arc sine of 0.5? What angle has a sine of 0.5? So the way you would do that graphically is you would draw a horizontal line at 0.5. You'd find the points of intersection with the sine function. You'd go here and read off the value. So if I plug this into my calculator, and I'm doing it in radians, so make sure your calculator's in radians. So if I just blindly do the arc sine of 0.5, I get 0.523 5 ... etc. So again, this is an example where this decimal doesn't immediately register. What does that mean? Whereas if I did it over here, I'd get in, if I had the scale right on the x-axis, I could read off pi over 6. So why is that not the same? Well, what you have to do is take this answer that you get and divide the answer by pi. So we do this, we did the calculation on this part. Oh, almost didn't save it here. Let me delete that. So I take the answer, I divide by pi, I get 0.1666 pi, which is pi divided by 6. And you can see that, on the unit circle, what angle has a sine of 0.5. So you remember that y-coordinate is the sine. So you come up here, oh, is there any of these points where the y value is a half? Oh yeah, there it is. What's the angle? 30 degrees, pi over 6. So that's how you would do it using the unit circle. Here we have the inverse tangent of negative square root of 3. So let's just plug that into our calculator. The inverse tangent, make sure you're in radians. The inverse tangent of negative the square root of 3. and I get negative 1.047. Okay, so leave that in your calculator. So again, we would take this number that I haven't deleted from my calculator yet and divide that number by pi, and I get negative 0.333 pi. So that's negative pi over 3. And again, if you go to the unit circle, if you look at, under what circumstances do I get the square root of 3? Well, that's where I'm taking the square root of 3 over 2 divided by a half. So these cancel out. So this is my y coordinate, this is my x coordinate. It's negative, and I know that in this quadrant that the y value is negative, so the negative is going to go with the numerator. And so what I look for is I look for the coordinates 1/2 comma negative the square root of 3 over 2, and you can see right here it is. And so the answer is, it says 30 degrees, but again, we're taking the angle relative to the positive x-axis, so it's not positive 5 pi over 3, it's negative pi over 3. Now, I mentioned this earlier, but here it is formally. If you need to do the arc secant, the arc cosine, and the arc cotangent, all you do is you take the arc cosine of 1 over the argument, and the same for the other two. So the angle whose secant is x is the same as the angle whose cosine is 1 over x. The angle whose cosecant is x is the same as the angle whose sine is 1 over x. The angle whose cotangent is x is the same as the angle whose tangent is x. And what we're trying to do is find an angle. So as long as we find the right angle, then we're good. That's what we're looking for. Okay, so apparently that's it for that section. So, watch your examples, which will be like the homework, and then do your homework. Turn in your homework. Send me your notes for the lecture. You don't need to send me the notes for the examples, but I would recommend that you do those to help you better understand what they're asking for the homework problems.